Hi, I'm Ryan. I'm going to do a talk on decoding the Solarwinds data exfiltration. So, what is Solarwinds? What is SUNBURST? I'll tell you. So, here's an overview. So, the Solarwinds attack was a supply chain attack, which means that they got into the supply chain. So, before the service was provided to the different enterprises, they were attacked, and through a malicious update, they sent the files to different organizations, including, let's see, Fortune 500 companies like Microsoft, Cisco, Intel, as well as different government agencies like the Pentagon, DHS, the State Department. So, pretty big, important organizations. And we'll see, it was initially compromised in September of 2019, but it wasn't really discovered until December 2020. So that was, oh man, over a year and over 9 months of like active uh, malicious activity. And up to 18,000 of their customers were affected. So why SolarWinds? What was SolarWinds? SolarWinds was a IT management system, and they had two different modes, two different services. One was the monitor mode, which let them look at performance, cloud services, organize the entire network, and one was the response mode, which is a more dangerous vector, which is they could map credentials, lay out different networks, move things around, that sort of thing. So it was, I mean, if you're managing the entire IT service, that is not something you're going to want to be compromised. So, what would happen if you compromise a service? There's a whole bunch of different options. One is that you could observe the different credentials for passing between different devices. You could reshape the network to capture traffic going in between different devices. And you could do man-in-middle attacks to do so, as well as lateral movement to different target systems. You go from the device to device and infect them, as well as move between devices between different organizations. So how did it begin? So in September 19th is when it started. Nobody knows exactly how they got into the website update server, but there was an intern who had access to the server, and on his public GitHub repository, he posted the password SolarWinds123. It was very secure, which was discovered by a researcher about a year before this, and it was up for almost 18 months. So that's not good. That's not good password security at all. It's probably something an insured should not have access to. They should rotate more regularly, all those sorts of things. SolarWinds denies that was the compromise, but you never know. So using that, in the website update server, there was an initial malware called Sunspot. It was uploaded. Now, Sunspot infiltrated between the security auditing of the final draft and the actual deployment. So at compile time, it injected the malicious code into the update. So what it did is it bypassed security audits, so no one who was monitoring the software saw it, but also got in before they did digital signatures. So it looked completely legitimate to any company who was downloading the update, which is very stealthy. And then distribution began in March of 2020, which is when the update was uploaded to the SolarWinds website. And we can see, so different sysadmin across these different organizations are responsible for downloading these updates, deploying them, making sure everything works. And that is how it happened to 18,000 of their customers. So what happens? How did it evade detection? So we see that the initial thing with the sysadmin to do is fetch and install updates of the SolarWinds Orion package. The Orion is the IT management service. And within the Orion package, there was a SolarWinds business layer.dll. Excuse me, there was a malicious executable within a DLL that was downloaded and implemented an HTTP backdoor. So what an HTTP backdoor does is let it communicate over the web with different services. So malicious actors can send messages back and forth. We'll look more into that later. And to evade detection, it had random sampling of the file creation time. And it would monitor that continuously until between 12 and 14 days, it would initiate. During that time, it would also enumerate the host. So look for different kinds of services, things as Window Defender, things like CrowdStrike EDR. So varying levels of sophistication of defense to know what stages it could progress towards. It would also know if it was running inside of a VM or a sandbox, so it could kind of scramble the different code, so it made analysis much harder when it was discovered. It also detected if the machine is connected to the web, so it could retrieve the domain address, and we'll see what it does with that later. And then it moves to executing the actual malware. So this is just the enumeration part of the attack. We haven't gotten into the malicious part yet. So who knows what a DLL is? Does anybody want to explain it? Yes.
It's a shared library, so it's code that can be loaded by other executables and run. And you only have to store it once instead of in every single executable. So it's more efficient in terms of storage.
Yeah, that's perfect. Yeah, he nailed it. That's it's just a shared library between different executables within the app, so it manages resources better. So what they did is they took one of these DLLs, one of these libraries, and within it they injected a Trojan. So it's like a legitimate DLL, but within it is a malicious executable. It would be called whenever one of these functions was called. And you can see it's being called by multiple different files within the system. So what did the malware do after it was executed? So remember, it had a 2-week dormancy, and then it contacts this domain, which you should not Google because it will cause alerts. But it asks for C2 commands using DNS tunneling. Does anybody know what C2 stands for? Anybody want to explain? Someone new? Come on. All right, I will. Command and control means that it's where it contacts the malicious actors. So it can send different commands to tell the malware what to do, how to, and we'll see that later, what kind of capabilities it had. And I'll explain DNS tunneling in much greater detail later on. But one of the highest level of escalation was to drop something called a teardrop malware, which is a memory-only dropper, meaning it only runs in RAM. So different EDRs, different sort of things like Windows Defender scan your files for malicious executables, but it does not scan your RAM. You need something much more sophisticated to scan your RAM, something like CrowdStrike services, things like that. So on a lot of computers, this was not detected. It was undetectable with the modern equipment. And that would download Cobalt Strike Beacon. So Cobalt Strike is a C2 framework, kind of like Metasploit. If you're familiar with Metasploit, Metasploit is open source, but C2 is much more closed source and is much more sophisticated, and it's used by more advanced penetration testers. So download that, and then it would use a fake JPEG file. So it would create a dummy file in your file system using JPEG. A lot of services did not scan JPEGs because they're looking for executables. So it XOR encrypt and hide it within a JPEG, so it's steganography. And then it could decrypt later and run different sorts of malicious executables from Beacon. And that would aid you with lateral movement, exfiltration, all sorts of things like that. Okay, DNS. Who knows what DNS is? This is a little easier. Okay, BJ, can you explain what DNS is?
Yeah, so I was in CEO's network fundamentals call, and so I learned all about this last week. It is domain name service, and so it's like we don't want to have to remember 8.8.8.8. We just want to be able to type in Google, and so it resolves all the domain names to their IP addresses, and it's fully distributed network networking. So there's like 13 root nodes that root servers out there with the domains, and then it all filters down to other servers. And so by going through those servers and asking, hey, what's this domain name supposed to be, we eventually figure out what the IP address and can see that website.
Exactly. Yeah, that's perfect. So I'll elaborate a little further. So we have the resolving server, which is going to be on the enterprises side. We have the root name server, which is the big broad one that he was talking about, and it kind of navigates this whole system. We have the TLD name server, so that is the like .com, .net, .edu. It searches for those, and then the authoritative name server, which is usually on the provider side. So another company owns the authoritative name server, and that is what brings together the whole domain. It brings a record, and then it takes those files from the website and brings it back to your PC so you can access the website. So DNS tunneling, here's how that can be maliciously used. So let's say you've been hacked and they have an HTTP backdoor. So they send an execute just a web URL to the DNS server, and let's say it's obfuscated. So it just looks like gibberish, but it bypasses the firewall because you can't really block DNS traffic. That would be highly restrictive. You can kind of scan for regularity, but a single DNS is probably not going to be caught unless it contains something obviously malicious. And that will spin to the web. The web will send it to this authoritative server owned by the bad guy. And that bad guy can take, just that like 36 character bit in front of your DNS. It can decrypt it. And then they can sort of send each other information back and forth via that way if they have a web shell. So that's very dangerous. So there have been attacks that have, you could exfiltrate entire data files if you want to, just by sending little bitty chunks at a time. So this is what we're going to take a deeper dive into later. So this is after the initial compromise we talked about, it sends little chunks of data to and from the C2 server. The C2 server sends back a little chunk of data as part of the URL to the computer. And those little commands going back and forth are telling the malware what to do so they can escalate. And these are the 4 different domains that were used by the DGA. So this is what we're going to decrypt in a second, but it would take a little bit of data, encrypt it, put it right here, and then send it to the bad guy. The bad guy would send it back and tell it what to do. And the different domains are used for different purposes. We'll see those in a second. So how was it discovered? So it was first discovered at FireEye. I think they were looking around and found that some of their tools were missing. They were just gone. So like, what happened? And then they looked into it, and they found the SUNBURST malware that was doing it, as well as the beacon. And they started checking DNS records for all of their customers just to see. And they found these weird-looking DNS records to the ASVM cloud server that was being used by the bad guys. And they published those, and there was sort of a race to see who can decrypt these to see what's happening all over the world. And part of those were discovering of the Treasury Department, the Pentagon, because you can catch all those DNS records because they're just through the internet. As long as they're HTTP, they're unencrypted. And they found it. And it was similar tactics have been used by other actors. So APT29, UNC2452, or my favorite is Cozy Bear, the CrowdStrike nomenclature, which is much cooler. So what did SolarWinds do? So the malicious executable, the malicious updates. Yeah, question?
So when you said that FireSide or FireEye found that some of their tools were missing, why were those tools missing? Was it like part of the malicious that they had to like swap some files out, or was something else?
Yes. So after So you saw the DNS control C2. It'll say, "Hey, drop a beacon," if they see some data or a domain they want. So it will drop beacon, and then beacon can create a SMB connection, and that can be used to copy files to and from the bad guys much faster than something like DNS with little chunks. So they were taking entire tools and just moving them to themselves because they wanted them. These are probably their latest greatest tools that they did not want to share with the public. Good question. They might have wanted to get rid of them because they knew they were about to get busted, and they were just screwing with people. But I don't know their motivation for that, honestly. So what did SolarWinds do? So the malicious update stayed on their website for like 3 days after FireEye made it public. So you could just download highly sophisticated Russian malware for a few days there, which is kind of cool. Kind of bad though. But then afterwards, they realized they took it down. The certificates were revoked for the new updates, and then they pushed a new update with better certificates that they knew was not infected about a week later. And pretty fast, 94% of them removed the vulnerability in 3 days, but it was up for about 9 months, which is pretty bad. So just to recap, so first is they install the update to their computer. Then the client downloads the malicious update, and that DLL is downloaded with the malicious executable inside of it. It generates random domains, and it sends different information. What tools are running on this computer? What domain is this computer connected to? Is it Microsoft? Is it Oracle? Is it the government? And if the victim is interesting enough to want to know them, then they would escalate. But if it was not, it would kill switch and destroy itself. So there's no evidence of it existing there. And then that's after it said, yes, this is interesting, we want to go further. Then it would drop teardrop, then it would drop beacon, and then it would start taking that data and sending it to themselves. And then you could do lateral movement, persistence mechanisms, all sorts of things. Yes?
For that hallucination, is that just like that buffer they had? It goes like, I think it was 7 days or something like that, to making the incision or exploding?
So this would be after the 14 days. So the 14 days, it just hid for a little bit. And then it activated. And then it would send what we'll see later in a second. So how is the C2 traffic decoded? That's what we're going to go on to next. So if you want to download these files, I put in the Discord, you'll be able to follow along. I think you'll have a much better time if you do that. Is that big enough? You guys see it well? Okay.
Brian, can you make it a little bit bigger for the recording?
A little bit bigger, okay. So how many of you guys have used something like Jupyter Notebook before? Okay, some of you. How many of you guys know Python? Relative. Okay, a lot of you. That's good. So I have created a decoder that was these DNS records are public. So different emergency response teams would download these DNS logs to take them down, and they would extract the host names. So you see those unique host names file that I've also put down there? You're going to want to press this folder right here, upload, look in your downloads, unique host names, and put them in the context so that it will run properly. So in order to execute a block, you want to press Shift-Enter on it. So these are just some imports we need, and I'm going to walk you guys through the decoder, and we're going to kind of do some fill-in-the-blank coding and just see what we figure out.
Where did you put the file?
It should be in the Discord in the announcements.
That's what I'm saying. Where do you enter it into Colab? I haven't used this. So I was putting a step behind you.
Oh.
I was asking where do I upload the file into Colab?
Oh. The window?
That's perfect. Thank you.
Yep.
I'm on.
Yeah, if you want to upload unique host names, you should download your own copy, not a viewer copy. And click here, file upload. So this is just we're going to start with just introduction. So each DNS query contained encoded information about the victim organization. So we're going to see what is we're going to load the domain names from where? Hit unique. Oh, dash. That's txt. And then it's just going to open. For those you don't know, how do you play with an array in Python? So colon, say from the start to how many do we want to print out? Let's say 10. So we have, in our unique host names file, we have 1,722 unique host names. Okay, here are the first 5 for analysis right here. So this is the encrypted chunk of data that's being sent back and forth to the command and control center. And these are the different host names that we saw earlier. So each of these contains secret information about the company that they're trying to sneakily send to themselves. So we'll move on to cell 2. So who is familiar with base 32? Who finished my workshop challenge? I know I helped a couple of you. Not very many. Okay. So I'll go back.
What did you put for the domain?
What do you mean?
When you were playing with the array, what did you? Because we have question marks out.
So I've done this one.
No, the domain. Yes, 10. Yeah, you added 10. Oh,
Okay, 10.
What does that do?
It just prints the first 5 domains. So it just says to take the first 5 entries of this file and print them. Yeah. So this is base 32. It maps different numbers to characters. So we have 0 maps to A, 1 maps to B, 2 maps to C, so on and so forth. What you can do if you want to be sneaky is you can scramble this, insert your own, and those types of things. And it's kind of tricky to figure out. So right here, I've included the scrambled alphabet. Oh, excuse me. This is the scrambled alphabet that was used by the base 32. So instead of A, they have P. Instead of B, they have H. So on and so forth. But right here, we want to put in the standard base 32. So A to Z, 2 to 7. So you just do it like this. So if we think about like DNS limitations and the different segmentation calculation logic we'll see later. So Sunburst is going to split the long domain names into multiple fragments. The malware has 36 possible segment positions, so 0 to 35, which aligns with 26 letters plus 10 numbers, so 36 possibilities. which is what you see right here. So this fill in the blank is going to be 36. Because if you think about it, one character, if you have all the ABCs and 10 digits, you have 36. Let's go ahead and print this, and this is what you should see right here. Everybody good on pace? Yes.
Why is it 36 segments? I understand that it's because of you only have so many letters and numbers, but why can't you repeat?
It's a good question. I think you'll see later.
Oh.
If you just after I go through it all, it'll be much more better explained. So this is where they did the antivirus protection detection. So one of those domain names has different encrypted information that contains these codes. And these codes mean certain things. So this one means Windows Defender is running, or Windows Defender is stopped. Because once some of those, if they have the response category, they are able to close different processes and shut them down. So if they were able to stop Windows Defender, it's into line, as well as CrowdStrike, some more sophisticated softwares, so on and so forth. Different status operations, status name split. So who knows how to parse strings in Python? All right. So normally you want to put something like the punctuation. This one, it'll be right here. So we're going to split Windows and running into two different substrings. And then let's say let's leave a buffer of about 20 characters. Right here, so just so we have some room. So these are the different security products that were tracked by SUNBURST. Right now, I'm just kind of like laying the groundwork so you can understand. We'll get into the more complicated stuff in a second. Right here, actually. So if you're familiar with Python, you're going to build a reverse dictionary for lookup. So you're going to map each one of these characters right here to a numerical value in bit form. So we have 0 maps to P, 0, 1 maps to H, so on and so forth, as we saw there. And we want to keep only the valid characters. So if it contains anything outside of that base 32 range, we're going to scrap it, because it's not for this particular mode. And if it's empty, we just nullify it so it doesn't mess up our algorithm later on. So this is where it gets a little bit more tricky. So how many bits can you represent with 32 characters? Or no, how many bits does it take to represent 32 characters? You math it out. I see 4, 5. It's base 32.
Yeah, but how is it represented numbering?
Binary.
It's not how any of this works.
Yes, we're trying to represent 32 different objects, so we have 32 different options. Those 32 different options can be measured with 5 different bits of binary. So we're going to loop through and look at every 5 bits. We're going to move them into a buffer. And if that buffer has fewer bits than the skip, we're going to line it. And if it has we're going to pin the value to the existing bits in the buffer. So when do we have a full byte? How many bits is in a byte? 8. So we're going to say 7, because we're going to include 0. And hold on. So to extract the lowest 8 bits, 1 byte from our buffer, we're going to use a bitwise and an OXFF. So we're going to write that right here. Because this is 8 ones. So we're going to bitwise AND it with 8 ones. And after extracting the 8 bytes, we need to shift the buffer right by 8 positions to remove the byte we just processed, making room for the next byte. So this one will be 8. What did I miss? I forgot to say it was hex. There we go.
What did you change?
I pushed the O because this is a hexadecimal FF. So we see here, if we want to decode this into binary and then flip that binary to hex, this is what we have right here. So this is the hex representative of this decoded. So there's another different cipher too called the substitution cipher. If you're familiar with that, you just like, this is just a simple swap. There is no alphabet, or it swaps different characters. You see here, where was it? So this is a substitution alphabet. So this is probably, I think this is 26. We just swap A for R, Q for B, 3 for C, so on. So we're going to go in here. So normal characters are shifted -4 positions in the substitution alphabet. Special characters represented use a 2-character sequence. It's like dashes, periods, hyphens, those sorts of things that can be in domain names. If the first character is in special characters, the second encodes which special character. Does that make sense? You see, so the first byte is special, and the second bit will tell you which special character it is. So let's see, we want to list accumulated decode characters for I. So we want to enumerate the different encoded strings that we have. If it has a skip next, so it means it has a special character, we're going to find the position in the alphabet for that character. So if it exists, we're going to map the alphabet index to the special character using modulo. So special index equals char index modulo length. So where are we indexing to? It's going to be the special characters, if you remember. So up here we have our list of special characters that might be in the domain. So we're indexed to those specific special characters, append it at the special index, reset the flag, and then move to the next character. So if the current character is a special character, the next character encodes the actual special character. So what should we set the flag to? So when we encounter a special character marker, the next character will encode which special character to use. So we set the flag to true to skip normal processing of the next character. So we'll return back to this function right here. So if it's a normal character shift by how many positions in the substitution alphabet? We talked about that earlier. that is 4. I forgot to mention a lot of these things like the alphabet and the shifting were discovered by reverse engineering. So they took those executables, they were downloaded from the website, the malicious update. They plugged in something like GDB, Pwn Tools, IDAPRO, and they looked through the assembly and found these sorts of codes. So these weren't just pulled directly from the DNS. From the link here, we append it to the decoded version to the actual different the domain name. Then we combine it into a single decoded string. So we're going to do a little test. Hopefully it works. Yes. So after that's all done, we have this right here, which we can Google. That's no longer available. Never mind. So now we're going to move on to some of how the different metadata was encoded. Here. So the first 16 characters contain an encrypted GUID and metadata. So this is the general user ID. So it identifies the victim organization and includes a timestamp. So these are just certain references for how the date times are working. So base 32 decodes the binary from the string. If it's not decoded, then it returns nothing. It just didn't work. One of the bytes contains an XOR key. Since it's the first one. Oh. So there's multiple steps in this. The first one contains an XOR key. Then we decrypt it using the XOR key. So everything except for the XOR key is XORed for decryption. We put a 1 right here. So everything after it is decrypted, and then we return that description. So we want to calculate the segment number for the multi-part domain messages. This is going to send in the 16th character of the subdomain and the first character, so we can return the different segments that we have. So if the character is 7 through 9, we want to do 58. So looking at an ASCII table, the ASCII value has a 58, which comes right after 9. So values less than 58 are digits 0 through 9. So we're going to put less than 58 right here. Keep going. So the subdomain that contains the GUID is the first 16. We talked about that. The subdomain that contains the XOR key is going to be 15, or the 16th one right here, so 15. The first 8 are going to be the GUID right here. It should work. So in this thing, in this little data, so this is going to be the unique identifier. This is what is XORed with, and this is the segment value. So that way we can piece these different informations together via the segment value right here. That's what we're going to do next. Oh, nope. So this is where we're going to extract the antivirus production status from the special SUNBURST domains. I will tell you, I thought I did it wrong at first, but I think a lot of the public data sets have been cleaned. So a lot of this value this information is available, because I'm sure Microsoft doesn't want you to know what kind of security tools it's running. So it's going to return 0, but it's not because you're doing it wrong. So if not decrypted, we weren't, so the high bit or hexadecimal 80, oops, which is going to be 1 with 7 zeros in binary of the XOR key is used as a flag. If this flag is set, that means it is not an AV status domain. So this is how it differentiates between the different domain types. Cap lock's on. We're going to extract it with the XOR operation right here. We're going to modulo what? So the GUID extraction uses an alternating XOR pattern. When I is even, we XOR with decrypted 10. When I is odd, we XOR with decrypt 9. So the modulo 2 is what makes this happen. So we can alternate between 8 and 9 depending on the flag. We're going to extract the timestamps and the flag. How many bits to shift right? So the upper 4 bits of the byte 8 contain the message type. Right shifting by 4 will extract these. So it's tracking it by half hours. So a half hour is 30 minutes. And so now we're going to extract, this is going to be the information the way it's sent. And now we're going to extract the AV if the products are present. Let's see. So the AV status messages have a specific length. So it's going to be 8 bytes for the GUID data, 3 bytes for the timestamp and flags, 2 bytes for the AV product flags, so 13 bytes total. And these can be contained over multiple different DNS requests and fragmented together. We're going to see here, no AV status domains found, probably because they are scrubbed for security reasons. And this is going to wrap up the domain encoder. So hopefully it will all start to make sense on this one, because it's been a bit all over the place for now. So it splits the domain into labels and takes the first subdomain. Right here, so it strips it. The subdomain must be longer than how many characters to contain the secure string plus the segment. So once again, it's 16. Because we need at least 15 characters for the secure string plus 1 for the segment number. Anything shorter cannot be a valid SUNBURST domain. After the 15 character secure string and 1 character segment number, everything from position 16 onward is in the encoded victim domain. So everything from 16 onward will be the domain for the victim. So we extract the GUID, switch it to hex, calculate the segment number for the multi-part messages. We're going to decode the domain part. Let's see, what prefix indicates base 32? Which is 00. So if it's 00, we know that it is base 32. Let's see, we use the decode. So if there's a presence of 0, which is a special character in the substitution cipher, that indicates that it is a substitution cipher, not the base 32 cipher we found earlier. So we try those. So what character indicates if it's a substitution cipher? That's just a regular 0 right here. Oops. 1 second. I did this incorrectly, sorry. So we find the flag first, and then 2 onward is everything after the prefix. And then this 0 right here is the flag that indicates the substitution cipher, whereas the double 0 indicates the base 32. So then it should return all of this, all relevant info. It should decode the domains. And this is just going through the list, doing the different processes. Let's see if it works. Here we go. So it takes that little chunk of information. It takes the GUID, the segment number, what kind of encoding it uses, and what the domain name is. So it will match these different togethers based on the order that it is. So the last thing we need to do is stitch them all together so that we can have full domains. If you see here, there's some smaller domains. Let's see, like belkin.com. They can be contained in a single DNS query. So if we Google that, I know this one works. So boom. So this was a company that was hacked that sells different iPhone chargers and phone accessories and things like that. So now we're going to reassemble from multiple SUNBURST DNS queries. Each domain fragment is going to contain, like we talked about, the GUID, the segment number, the decoded victim domain fragment. And the fragments with the same GUID are combined in segment order to reconstruct the original victim domain. And then we're going to give, so this is the full list of domains, which is going to return a tuple of the fully assembled and then the AV status information, which we know is going to be 0. So we're going to place each decoded fragment at its segment position in the array. This ensures that fragments are automatically in the correct order. So we're just going to put oops, did I miss something? Oh, excuse me. So we established earlier that the max segment is 33. We create a list with 33 segment empty slots to hold fragments in their correct position. The dictionary storing the antivirus status information for each GUID is right here. We're going to decode each domain, sort into fragments. So which field tells us the position? If we look at the decode SUNBURST domains function return structure, the number is stored in the segment field. So it's determining which number it is for the GUID, how we can reconstruct them all. We're going to do it again right here. So we take the GUID, the segment, and then we place it right here. We want to reassemble by the GUID, combine the fragments. And if you don't, so you combine strings is we do dot join. That should be it. I'm missing one. So it creates a star if it is incomplete. So we know that these have information that continues going on. We saw Belkin was a full one, gncu.local was a full one, so on. So from there, we can kind of reassemble them all together. And this one is just the statistical analysis of the whole data set. If I run this one, we see that there are 390 unique GUIDs. Of them, we can reconstruct 127 domain names, and there are 263 fragments that have not been organized. Here's our top-level victims.com, .local, .org, .net, and I sorted these top-level domains into the different sectors. We saw 3 in the education, 3 in the government, 5 healthcare, and 30 corporate. That's it. That's all my talk. I know it's kind of dense if you want to look it over, but I think it's pretty cool to piece these things together because it does get quite complicated. Thank you. Yes.
I have a question.
Yeah.
So you just wrote this in Python. What language was the original language? Like the malware written in?
I don't know. That's a good question. I think it was not C#. I know some of the decoders are written in C#. I can't answer that. Sorry.
No worries. I've got another question.
Yeah.
So what we basically did is we like took whatever data that we want to exfiltrate, we inserted it into the subdomain URL, and then we pulled it out. And, like we watched how they did that. That was the process.
Yeah. So when you just pull DNS records and there's a bunch of gibberish going to these domains, that whole process is super convoluted to hide what's going on. So yes, we just pull all that information out of the domain. Thank you. Yes.
Is there like a way that they start analyzing the gibberish?
Probably reverse engineering the executable update just to see what's going on. There were a lot of different efforts. You could do some statistical analysis because a lot of this could be broken with frequency analysis if you were to gather enough data. I don't know exactly how that was done. Anyone else? Questions? Yes.
How would theoretically a corporation stop this? Because it seems like anybody could like steal proprietary information, curl or send out DNS requests, and then just start exfiltrating information if they don't have like some sort of DNS filtering on their network.
Yeah, they would monitor. That's a good question. I think they have DNS filters to look at frequency. Exactly how they would do that, I don't know, because you can't really create a blacklist, or you can't really create a whitelist unless you're in something like a SCIF, because that's going to be severely limiting. You could create a blacklist, which is probably what there's there now, but actually how to catch it, I'm honestly not even sure. I think that's it.
One more for Ryan.
Yes.
Like if it was a particularly long domain name, you could flag it, and then that limits how much data they can exfiltrate, like the rate.
Yeah, maybe because you have 36 segments. You split it across. You see multiple visits. I don't know. Thank you for coming.
Awesome. Thank you, Ryan.
Yeah.